Hello friends, I welcome you to my lecture on equations with convolution type kernels. There will be two lectures on this topic. So, this is first of these two lectures. Let us consider the linear integral equations with convolution type kernels. Let us take two functions phi 1x and phi 2x which are defined for x greater than or equal to 0 and are continuous. Then the convolution of these two functions phi 1x and phi 2x is defined by a function phi 3x equal to integral 0 to x phi 1x minus t into phi 2 t dt. It turns out that the function phi 3x is also continuous for x greater than or equal to 0. Let us say that the Laplace transforms of the functions phi 1x and phi 2x be denoted by phi 1s and phi 2s respectively, so that L phi 1x is equal to phi 1s and L phi 2x equal to phi 2s. Then by the convolution theorem for the Laplace transforms, we have Laplace transform of phi 3x, that is Laplace transform of this is phi 3x. So, Laplace transform of phi 3x is the product of the Laplace transforms of phi 1x and phi 2x, which is equal to phi 1s into phi 2s. Now, let us consider the Volterra-type integral equation of the second kind, yx equal to fx plus integral 0 to x kx minus t by t dt. So, here fx is a known function, kx minus t is also known. This kernel of the integral equation k is solely dependent on the difference x minus t of the arguments t and x, and then you have yt, the unknown function. So, let us see how we can solve such an integral equation. Such an integral equation where the kernel kxt is solely dependent on the difference of the arguments x and t, that is x minus t, is called an integral equation with convolution type kernels. So, what we will do is okay, so let us say let fx and kxt be sufficiently smooth functions such that as x goes to infinity mod of fx is less than or equal to m1 times e to the power alpha 1x, mod of kxt is less than or equal to e2 times m2 times e to the power alpha 2x. That means fx and kxt are both of exponential order. Then using the method of successive approximation, it turns out that mod of yx is less than or equal to m3 times e to the power alpha 3x. Now, consequently, the Laplace transforms of fx, kxt and yx exist. Let us assume that Laplace transform of fx is fs and Laplace transform of kxt is k tilde s, and Laplace transform of yx is equal to s. Here remember that kxt is a kernel of the type x minus t, where that means kxt is a function of x minus t. So, what we will do is, let us take the Laplace transform of both sides of the equation 1. When you take the Laplace transform of this equation 1, Laplace transform of yx will be by s, which will be equal to Laplace transform of fx, which we have assumed as equal to fx, and then Laplace transform of integral 0 to x kx minus t by t dt, which by making use of the convolution theorem for Laplace transforms, we can write as the product of the Laplace transform of kxt and yt. So, this will be equal to ys equal to fs plus Laplace transform of kxt, which we have assumed as k tilde s into ys. Then we can solve this equation for ys, and ys will be equal to fs over 1 minus k tilde s, where we are assuming that k tilde s is not equal to 1. So, then the solution yx of the integral equation 1 is found by taking the inverse Laplace transform of ys, that is we get yx equal to L inverse by s. Now, let us see how we apply this method to solve a integral equation of Volterra type, second kind. So let us consider the integral equation phi x equal to sin x plus 2 times integral 0 to x cos x minus t phi t dt. So let us take the Laplace transform of both sides. So then Laplace transform of both sides when we take, we will get Laplace transform of phi x equal to Laplace transform of sin x plus 2 times Laplace transform of this convolution of cos x and phi x. So 0 to x cos x minus t into phi t dt, or we can say phi s is equal to 1 over s square plus 1 plus 2 times Laplace transform of cos x into Laplace transform of phi x, or we can say phi s equal to 1 by s square plus 1 2 times s over s square plus 1 into phi s. Let us collect the coefficient of phi s. So phi s times 1 minus 2s over s square plus 1 equal to 1 over s square plus 1, or we can say phi s times s minus 1 whole square divided by s square plus 1 is equal to 1 over s square plus 1, or we can say phi s equal to 1 over s minus 1 whole square. Now let us so then phi x, the unknown function phi x is obtained by taking inverse Laplace transform of 1 over s minus 1 whole square. Now let us recall that Laplace transform of t is equal to 1 over s square. Laplace transform of t is 1 over s square, and by the first shifting theorem, when you multiply t by e to the power t, s is replaced by s minus 1. So we get 1 over s minus 1 whole square. So thus we can say that hence L inverse of 1 over s minus 1 whole square is equal to t e to the power t. Now here this is the function of phi x, phi is the function of x, so I can write it as x times e to the power x. Thus the solution of the integral equation phi x equal to sin x plus 2 times integral 0 to x cos x minus t phi t dt will be equal to x e to the power phi x equal to x e to power x. Now let us take one more example on this. Consider the Volterra integral equation of the second kind, phi x equal to e to the power 2x plus integral 0 to x e to the power t minus x phi t dt. Okay, so we will be solving it by the by taking the Laplace transform of both sides, but here let us notice that when we compare it with the standard Volterra integral equation of second kind with convolution type kernel, here we should be having phi x equal to fx plus integral 0 to x k x minus t phi t dt. So, instead of t minus x, we should be having x minus t. So, what we write is, we can write the given equation as phi x equal to e to the power 2x plus integral 0 to x e to the power minus x minus t into phi t dt. So, kxt is e to the power minus x minus t. Now, let us take Laplace transform both sides. So, taking Laplace transform, both sides of the above equation, we have phi s equal to, phi s is Laplace transform of phi x, then Laplace transform of e to the power 2x is 1 over s minus 2 plus Laplace transform of the convolution 0 to x e to power minus x minus t phi t dt. So, this is Laplace transform of e to the power minus x into Laplace transform of phi x, and so we can write it as R phi s times 1 minus 1 over s plus 1 equal to 1 over s minus 2. So, I will have s over s plus 1 1 over s minus 2, or phi s equal to s plus 1 divided by s into s minus 2. We can break it into partial fractions. So, okay. So, a upon s plus b upon s minus 2. Then a is given by s plus 1 over s minus 2 at s equal to 0. So, we have minus half, and b is equal to s plus 1 by s at s equal to 2. So, it is 3 by 2. So, thus we get phi s equal to so hence phi s is equal to minus 1 by 2 into s plus 3 by 2 s minus 2. Now, let us take inverse Laplace, taking inverse Laplace transform both sides. L inverse phi s equal to L in minus half L inverse 1 by s plus 3 by 2 L inverse 1 over s minus 2, which gives us the solution of the given integral equation. So phi x equal to minus 1 by 2, L inverse of 1 by s is equal to 1. So we get 1 plus 3 by 2, L inverse of 1 over s minus 2 is e to the power 2x. So we get phi x equal to minus half plus 3 by 2 e to the power 2x. This is the solution of the given integral equation. Okay, now one more problem I have taken here, I can discuss it here. Phi x equal to x minus 0 to x sin hyperbolic x minus t phi t dt. When we take Laplace transform of both sides, Laplace transform of phi x is phi s, Laplace transform of x is 1 over s square minus Laplace transform of sin hyperbolic x, and Laplace transform of sin hyperbolic x is 1 over s square minus 1 into Laplace transform of phi x, which is phi s. So we can then collect the coefficient of phi s, which is 1 plus 1 over s square minus 1, and then divide by the coefficient of phi s. So we get phi s equal to 1 over s square minus 1 over s to the power 4, and then we can take the inverse Laplace transform of this equation. So L inverse of phi s gives us phi x, and L inverse of 1 over s square is x, L inverse of 1 over x to s to the power 4 is x cube by 6. So the solution of the given Volterra integral equation of convolution type is phi x equal to x minus x cube by 6. Now there is one more equation, phi x equal to 1 minus 2x minus 4x square plus integral. This is a problem which let us do here. So phi x is equal to 1 minus 2x minus 4x square plus integral 0 to x 3 plus 6x minus t minus 4x minus t whole square into phi t dt. In my lecture on Volterra integral equations of second kind where kxt is of some special forms, there we had discussed this problem because the kernel here is a polynomial in t of degree 2. So we can solve it by the method which we discussed there, but you will see now that when we solve this by using the Laplace transform, the solution of the this integral equation comes very easily. So let us take the Laplace transform of this. So taking Laplace transform on both sides, we get phi s Laplace transform of 1, which is 1 by s, minus 2 times Laplace transform of x is 1 over s square, minus 4 times Laplace transform of x square is Laplace transform of t to the power n is equal to n factorial divided by s to the power n plus 1. So Laplace transform of x square is 2 factorial, that is 2 factorial divided by s to the power 3 plus Laplace transform of this convolution. So Laplace transform of 3 plus 6x minus 4x square into Laplace transform of phi x. So what we get is phi s equal to 1 over s minus 2 over s square minus 8 over s cube plus Laplace transform of 3 plus 6x minus 4x square is 3 by s plus 6 by s square minus 4 into 2 factorial divided by s cube into phi s. We can then collect the coefficient of phi s. So, what we get is 1 minus 3 by s minus 6 by s square plus 8 by s cube equal to 1 by s minus 2 by s square minus 8 by s cube. Let us take LCM there. So, we get s cube and then we get s square minus 2s minus 8. So, solving we have simplifying we get phi s times s cube, we have s cube minus 3s square minus 6s plus 8. This is equal to s square minus 2s minus 8 divided by s cube. Now, so phi s is equal to s square minus 2s minus 8 divided by s cube minus 3s square minus 6s plus 8. Now, we can see that the denominator is a polynomial of degree 3 in s and s is equal to 1 is a root of this polynomial, because when you put s equal to 1 what we have is 1 minus 3 minus 6 plus 8. So, s equal to 1 is a root of this polynomial. So, s minus 1 is a factor, and when you divide it by s minus 1 what you get is s square minus 2s minus 8. So, s square minus 2s minus 8 divided by s minus 1, the denominator can be written as s minus 1 into s square minus 2s minus 8. So, we can cancel this and we get 1 over s minus 1. Now, phi s is equal to 1 over s minus 1. So, taking inverse Laplace transform, so L inverse of phi s is equal to L inverse of 1 over s minus 1, which implies phi x equal to e to the power x. So, phi x is equal to e to power x is the solution of the given Volterra integral equation of second kind. So, when we discuss this problem there, when kxt is of some particular form, there the solution was quite lengthy, but you can see here that by taking the inverse Laplace transform, we can use the by using the Laplace transform we can find the solution of this Volterra integral equation very easily. Now, let us consider a system of Volterra-type integral equations. A system of Volterra-type integral equations can also be solved by making use of the Laplace transformation. So, let us see how we solve a system of Volterra-type integral equations of second kind. Let us consider a system of Volterra-type integral equations by I x equal to f I x plus sigma j equal to 1 to n integral 0 to x k I j x minus t by j t dt. So, there are n integral equations here, and therefore, there are n functions to be determined. The functions, unknown functions are by I x, where I runs from 1 to n. So, there are n integral equations, and therefore, there are n unknown functions by I x, and the functions f I x for I equal to 1 to n and the functions k I j x are known functions of known continuous functions whose Laplace transforms exist. So, we are assuming that the Laplace transforms of the kernel and the function unknown and the known function f I x are do exist, and then what we do is we take the Laplace transform of both sides of this equation. When you take Laplace transform of both sides here, what you get is, let us denote Laplace transform by x by I x by capital by I s and the Laplace transform of f I x by capital F(I)s, and then we have sigma j equal to 1 to n. This is convolution of Kijx and by jx. So, product of the Laplace transforms of Kijx and by jx. So, Laplace transform of Kijx we are denoting by Kij tilde s, and Laplace transform of by jx we are denoting by js. So, here we are denoting a Laplace transform of Fix by Fis, Laplace transform of by Ix by Is, and Laplace transform of Kij. So, this is what we have, and then we will have these n equations. So, this is a system of linear algebraic equation in by Is. You can see here this is a system of linear algebraic equations in by Is, and we shall solve this linear system and to determine the expressions for this function by Is, and then we will take the inverse Laplace transform of by Is to get the function known function by Ix for I equal to 1, 2, 3 and so on up to n. Let us say for example, we consider this system of algebraic equations. Phi 1 x equal to 1 minus 2 times integral 0 to x e to the power 2 times x minus t phi 1 t dt plus integral 0 to x phi 2 t dt, and the second equation is phi 2 x equal to 4 x minus integral 0 to x phi 1 t dt plus 4 times integral 0 to x minus t phi 2 t dt. Then, so we get a system of linear algebraic equations in by Is. There will be n equations in the unknown functions by Is. We can determine the unknown functions by Is from these n equations, and then in order to find the solution of the given system, we will then take the inverse Laplace transform of by Is. So, taking inverse Laplace transform of by Is will determine the unknown function by Ix for I equal to 1, 2, 3 and so on up to n, which gives us the solution of the original system 2 of integral equations. We have given an example. Consider the system of algebraic equations phi 1 x equal to 1 minus 2 times integral 0 to x e to the power 2 x minus t phi 1 t dt plus integral 0 to x phi 2 t dt, and phi 2 x equal to 4 x minus integral 0 to x phi 1 t dt plus 4 times integral 0 to x minus t phi 2 t dt. So, here there are two unknown functions phi 1 x and phi 2 x. We will be taking the Laplace transform of these two integral equations, and then we will get the unknown functions phi 1 s and phi 2 s. The unknown phi 1 s and phi 2 s will be determined from the two linear algebraic equations in phi 1 s and phi 2 s, and we shall be taking their inverse Laplace transform to determine the unknown functions phi 1 x and phi 2 x. With this I would like to conclude my lecture. Thank you very much for your attention.